Okay, welcome back to part 5. Now, my view here is that the way that we do the quotients should be done in a particular style. And the style that I'm interested in isn't this testing the interval method. It relies far too heavily on your interpretation. This method is an older method also, but it's one that's proven over a lot of time spent with students in the HSC. So this would be my preferred method. Now, in this particular case, there's a little document that I've posted that should help you understand where we're coming from here. So, methods of inequalities. And basically what we're going to do is look at quotient and see what the quotients do in terms of understanding how they unpack. So what I'll do is bring up the one that's showing up here at the moment and just put that side by side, and that'll be something that we'll be able to refer to if we need to. Alright, so in this particular case, what we've got here is a quotient. This is the method that I'd prefer that you used, okay? So in the measurement of the inequality, it doesn't really matter that we don't understand. These are shifted values. These are a composite function. So composite functions are complex. It's not at this composite functions are complex, okay? Well, let's call it what it is, difficult, okay? But you know what? Not doing this, not the inequalities. If you were to plot that and do some work on that, you would need all calculus and other things, okay? But not for inequalities. For a quotient method, essentially what we want to do is test the case when the denominator is positive and when it is negative. That's what we want to do. We want to check those two values because the effect of the negative denominator is to turn around this inequality. So that's quite an interesting concept, isn't it? That's quite an interesting concept and one that we'll get used to as time goes on. Alright, so what we're going to do here is we're going to understand that we're going to, it's already been normalised, so that's the first step in the process. That is, put everything to 0 on the right hand side. Well, it's already got 0 there, so we can tick that, okay? And then we go straight and have a look at the analysis of this. So what I'm going to do is treat this like a positive denominator. So the numerator would be x plus 1 is greater than or equal to 0. So that won't change. Intersected with the denominator, which is also positive. We're calling that. We're designing that. We're saying, hey, positive. Okay? That's what we're saying. Over here, we're going to say that the numerator is dependent entirely on the denominator. And in this case, we're saying the denominator is negative. So it will always be the case in these, regardless of what's happening with the inequality, that these guys are in terms of a single positive-negative inequation. Okay? Over here, it'll still have its original inequation element, but in this case here, it's turned around. Why? Because this is negative. This says the denominator is negative, doesn't it? X minus 2 is the denominator. It's negative. So all we need to do then is a couple of simple operations to understand what's happening. Okay? So x plus 1 is greater than 0, so we'll subtract 1 from both sides. So x is greater than or equal to 0. Over here we can add 2. So x is greater than 0. Greater than 2. Okay. So in this case here, when we draw our number line, we've got 0. And sorry, that's minus 1, isn't it? I just keep ignoring those. That's my dyslexia, dysfunction playing up. So there's my minus 1 and my 0, 1, 2. So what's happening there? Well, we're including minus 1 and we're saying to the right, please, off you go, x is greater than -1. There you go. For this one here, x is just greater than 2, not included. So off you go, please. So where the intersection is, where both of these are happening. This is the intersection. Okay, this region here is the intersection. So the solution to this is only the one that's over here. The intersection of these occurs at x, but as we can't include 2, the solution, therefore, is x is greater than 2. Okay? Now let's have a look at this one. We've got to process this in exactly the same way. So we'll take away the negative, and so x is less than or equal to -1. In intersection with this one, we'll add 2. So x is less than 2. So when we come to do our number line, we've got -1 and 2 again. This one is saying x is less than -2, so we pick all of that up, and off you go. Okay, and we'll put the intersection in just to remind ourselves we're doing both. And this one's less than or equal to -1, so we're going to put our -1, and there's the boundary. The boundary has been established. Okay, so we're including -1. So the solution for this side is that x is less than or equal to -1. So this is the one that makes this life a fair bit easier. So between x is less than -1, so there's -1, and x is greater than 2, what do we see? X is greater than 2, and x is less than -1, inclusive. What's the interval? The overall solution is that we can't have. We've got an empty set. There aren't any values that pull that together. Okay? So this is a much easier way to recognise what's happening than using the testing method that we did with the others. Okay? So it's the null set or the empty set. And we just do that. Okay? So the overall solution is there aren't any values for which this is true. Okay? So we just need to take the confidence that when we see that there's no intersection, so this interval means no intersection. So there's no values that make sense for this. Okay? Now if we were to plot this on Wolfram, beware, when you do something like this, it can be quite confronting. So when we plot this and do our x minus 1 and our x plus 1, it's going to be looking terribly, terribly unfamiliar. Okay, and I'm not bothered by that. I'm not bothered by that at all because I've released you from this burden of saying, now come on, we've got to kind of do all of these things. Well, this is an introduction to an analysis idea. So we put the equal afterwards and we have a look at this and see what it looks like. Okay. So there are our solutions. And there are our split non-intersected values. Okay, there are our split non-intersected values. So what we find, if we plot, this is a composite function. Okay, this is a composite function. And so it's an amalgam of x plus 1, which is a linear, and 1 over x minus 2, which is a product. So this is very unfamiliar for you. Okay, and so we need to be clear on this. So this is the solution set we got. Okay, very much the same thing. All right, the solution set in terms of inequality is that there's no intersection. Certainly there's some parts of the graph which are above and below, but there are some that are not. So there's no intersection of this, okay? Or if you like, that is the answer for the positive aspects of the graph. Okay, the positive aspects take hold in these two separate entities, which is another way to interpret that. Okay, there's no intersection, but it's positive there and it's positive there. All right, so it's a very simple method in that sense. Okay, very, very simple method in that sense. Nothing for us to get too excited about or too complicated about. It's just a very straightforward process. Okay. Now, obviously, whenever you're doing any kind of maths at uni, you're going to be confronted with some things. So we're going to normalise this. So we're going to minus 3 to both sides. So we've got x over x plus 1 minus 3 is less than 0. Now look at this. Oh boy, adding fractions. We're adding fractions, so we need to multiply by same family. This is over 1. So what would we multiply this one by? We multiply it by x plus 1. What you do to the bottom, you do to the top. So this is very advanced, but it's still adding fractions. Okay, now there's an expansion to be had, and they're on the same family. The same family as x plus 1. So we've got an x over there. We've got a minus. Now let's put a bracket in. 3x plus 3, and do the expansion of the minus sign, just so that we don't lose sight of that. So we get x minus 3x minus 3 over x plus 1 is less than 0. So now we've got our, is there anything that can be changed there? No, I don't think so. Okay, and all we're going to do is now test our values. Plus x, so last thing is minus 2x minus 3 over x plus 1. Just an orange and minus 3 oranges. All right, so we test for plus and minus denominators. Okay, plus and minus denominators. That's all we're testing for. So we want minus 2x minus 3 is less than 0, intersected with x plus 1 is positive. We want minus 2x minus 3 and 0 intersected with the denominator is now negative. So that's what that means. So that means this one is going to about face, because that's the rule. We're dividing through by a negative. There's your negative, minus that x plus 1, that x variable is changing, and so it's a little bit complicated. All right, so what we'll do is we'll put minus 2x. We'll leave minus 2x there, I don't mind. We'll add 3 to both sides, subtract 1 from both sides. So we'll have minus 2x, 3 intersection, x is greater than negative 1. Divide by minus 2, be careful. So x will be, swap that around, minus 3 on 2, intersected with x is greater than minus 1. So if we come to do the plot for this one, we'll have minus 1.5 and negative 1. X is greater than equal to, so not included, off you go. Not included, off you go. And so we found the boundary, and the boundary is x is greater than minus 1. So that's that side. Now let's do it for this side, because we want to check the intersection of both of these. And so we'll do the same thing. We'll add 3. Minus 2x is greater than 3, intersected with subtracting 1, because we were dividing by negative. Dividing by minus 2, be careful, changes it. So minus 3 on 2 intersected with x is less than minus 1. So when we draw this at minus 1 and minus 1.5, we go left both ways and left both ways. And the intersection of those two is this boundary point. And so we get x is less than minus 3 on 2. So for this particular set of equations, we've established that when x is less than minus 3 on 2, and x is greater than 1. So what we're going to do is 1.5. I'm going to flip that around. So I'm going to put minus 3 on 2x, and now I can join those together. Okay, and so what we'll have overall is minus 3 on 2, which is minus 1.5. So minus 3 on 2 is greater than x. It's greater than minus 1, or x is less than minus 1. So we can swap these around. Just got to think about that for a moment. If I put this one as minus 1x, no, I don't want to do that because they're not intersecting. They're not intersecting, so we're going to take it at face value. Okay, so we'll take the values at face value. So for this particular case, there's no intersection. There's no overall intersection. And so the answer is, so for minus 1, for minus 1.5, we get x is less than minus 1.5, so that's that one. And so this one here will be minus 1 is less than x. So there's no intersection. So the overall solution. But there are your two values. That's this is the boundary point. So to the left of the boundary point and to the right of the boundary point, we've got our inequality working. Okay, so that'll answer that. Now you can check these. Don't be afraid to check them. Okay, I don't mind you using technology to check them. Okay, so we're doing x over x plus 1. Is less than 3. Okay, and your values will fit. Okay, there are your two distinct values. There's no intersection. X is greater than -1. Well, that's what we worked out. X is greater than -1. Tick. And also, x was less than minus 1.5. There it is. So there's that break in there. So we've managed to do it quite readily and quite easily. So I like the testing of the intervals idea, but I like following procedures. You can do the testing of the intervals if you want to, but I think it gets very confusing. Mainly because you've got to pick up when the thing's not defined. Here, this is a much easier process. I hope you agree. All right, so we'll do, there's a sequences will be next week. So we'll do this one here. And so it's pretty straightforward for us. But again, it's just understanding. So we're going to put this into 0 on the right-hand side. So what you do to one side, you do to the other. Minus 1 is greater than or equal to 0. Goodness gracious, we've got to make this x plus 6. What you do to the bottom, you do to the top. So I'm going to miss a couple of steps. Minus x minus 6. 2x minus 3 minus x minus 6 over x plus 6, same family. Okay, then we've got minus x, so we've got x on the top. Minus 3 minus 6 is minus 9 over x plus 6. That's the one that we're going to test. Okay, so we're going to test for a positive and a negative denominator. So we'll have x minus 9 is greater than or equal to 0, intersected with the denominator, which is positive. And I'd say that by doing that. We're doing x minus 9 and 0, intersected with a negative denominator. Okay, there's our negative denominator, so that means this turns around. And that's the hard part of this, remembering to turn those things around. So adding 9 to both sides, x is greater than 9, intersected with subtracting 6, x is greater than minus 6. So we come to draw the line. We'll have minus 6 and 9 will be up here somewhere. If 0 is about there. So x is greater than 9, inclusive. Off you go. And x is greater than minus 6, not inclusive. Off you go. And there's the boundary. Okay. Over here we add 9 again. So you get used to doing the same thing. It's pretty mundane, isn't it? X is less than or equal to 9, this time intersected with x is less than minus 6. We're going to do our same thing here. And minus 6. So x is less than or equal to 9, so we call that in, it's inclusive. Off you go. And x is less than, so it's not inclusive, and off you go. So there's our boundary. Okay, a not included and an included boundary. So what we're saying is that the 9 values are included, but the minus 6 values are not. And if we go ahead and put that into Wolfram again, 2x minus 3, 2x minus 3 over x plus 6 this time. And we just want it to be greater than or equal to 1. What we'll see is where it's positive. So it'd be better if we could get, but our solutions are the same, minus 6 and greater than 9. So there are two separate sets of data. So if I get that minus 10 and plus 10, just do this between x is minus 10 and plus 10. I'm sure I pressed the wrong value there. Don't progress me, plot me. Now what did you do? 2x minus 3x plus 6. Greater than 1. But you didn't do, what did you do there? You need a column, a space. Sorry, I just did the wrong entry into Wolfram, that's all it was. So between minus 10. So there you can see the blocks of what's positive and what's negative, okay? And if we do the solution, it gives you exactly the same values. And what are the things that are greater than 1? And where are they? And what are the values? Minus 6 is the value, okay? And this value up here. So we can make that a bit more. Let's make that 20. Just for the sake of completeness, we've got time on a video to do that kind of thing. So there are our two regions where our curve, 2x minus 3 plus 6, which is a difficult curve, has values at greater than 1. Okay, now where is it asymptotic? It's asymptotic because the denominator can't be 0. The denominator can't be 0, so there's some manipulation that needs to be done there. But we take complex elements and do them this way, and we get the solutions. Okay, so in this case here, x had to be greater than or equal to 9, inclusive, and x had to be less than 6. And both of those points were our solutions for these inequations. Now, it's very, very easy. It's very easy to process doing this. So I really encourage you to pick that up. You can do you can get lost in the interpretation because of the complexity of those. Okay, so that's a method that just works. Now, in this method also, I've also put into play another common way of doing this is in the HSC is to squaring the denominator. So this is an alternative method. If you've done it and you wondered what it was all about, you might want to have a read through that as well. You can do that, but I think this is more difficult because it's prone to algebraic errors because you're multiplying by a square and expanding and doing all of that gathering. And then there's an interpretive element, just like the old-fashioned putting it into segments or areas and analysing the areas that way. I think the other method is a much more sound way to deal with those as well. All right, so that brings us to the end of this week. I'll do some shoot recordings as well, and we'll be away. I'll see you next time.